Hi, friends. Welcome to another episode of For Your Reference. This is the web series where we take a look at the Rust programming language. The target audience of this video series is basically beginner Rust programmers, maybe like a little bit more than beginners, like maybe you've written one or two programs and you just want to learn more. And so in this episode, we're going to be taking... This is definitely a episode you want to watch after watching the previous part. So I believe this is part 4. Is that correct, Noah? I'm not sure exactly what part it is, but the part right before this, we talked about ownership. And we're going to go take that a little bit further. We realize that ownership is cool because it gives us some memory safety properties that we like in programs, but it can kind of be a little bit awkward, right? And Rust has this concept of references and borrowing, and so that's what we're going to be dealing with in this video. How exactly Rust gets around this and makes this more ergonomic, and also at the same time still gives us all those safety guarantees that we love so much and the rigor that we probably are using Rust for. So anyway, joining me as always is my friend Noah. How are you?
Good, man. How are you doing?
I'm hanging in there, man. I'm pretty excited actually about this video. I think this one and the previous one are sort of my favorite topic in Rust, and also probably the thing that people get most nervous about because they probably heard some horror stories about like the borrow checker and the Rust tax and all this stuff. So how do you feel about this, having taken a look at this prior?
Yeah, I mean, I'd say I think it helps to have somebody who knows how it works explaining it, because I think just reading about it is not quite enough. So yeah, I hope this will help people to kind of get these concepts down.
Yeah. And I think this is definitely something that you want, like maybe a little, it's like one of those things in programming that has like maybe a little bit of a tacit feel to it, where, you know, writing some programs and gaining some intuition of how things will work, and maybe that will influence your design. And I think maybe we can talk about this a little bit real quick before we dive into things. I think one of the more sound complaints I've heard against the design of Rust is that it prevents, or it makes some kinds of experimentation a little bit harder. And so as a result, you know, you have to have some intuition ahead of designing your program. Like, this will work out because I haven't violated any of these rules or whatever. And I think people who like to experiment might, you know, sort of not like Rust in this way, right?
But they might be doing something dangerous.
Correct. And we will definitely talk about sort of just generally pessimistic and optimistic compilers, and, you know, what that means, and how Rust is definitely a pessimistic compiler, and so why that might be kind of frustrating, for instance.
Yeah. There's something I encounter a lot too, like I think with TypeScript and JavaScript. Like people have used JavaScript before, like they get frustrated with TypeScript because you know, the program's invalid now that was working for them, but it may not have been totally valid in all cases.
And so TypeScript, I'm kind of glad you brought this up a little bit, is TypeScript is a pretty unique example as far as compilers are concerned, because most compilers are either basically like, you know, sort of totally optimistic or totally pessimistic. TypeScript, I mean, maybe, you know, some formal like programming language nerd out there is going to be laughing at what I'm about to say, but you know, like I think that TypeScript is kind of weird because it's like in this like, it tries really, really hard to give you the pessimism when you want it and you want that rigor, but also tries to be optimistic for this experimentation, and also to make those JavaScript people feel more comfortable, right? So it's funny that you bring that up.
But yeah, the people the only experience I've had is people just getting mad.
So maybe it's just not doing a good enough job, you know?
Yeah.
Okay.
Cool.
All right. So
go ahead now.
Yeah. Let's just delve into this real quick. So this program here, we're going to be doing exactly what we did in the last episode. And again, I highly recommend that if you haven't seen the last video, you definitely go check that out, because this video is certainly not going to make a tremendous amount of sense without the other one. I think that in general, most of the videos in this web series you can kind of watch in any order, but this one sort of you need the previous one, the one on ownership, to really figure out. And so this is all review from that, which is that we learned about how bindings in Rust, and I think in the last episode I called them bindings, and I said I really like the name binding because bindings sort of the name implies that like, oh, this name is like bound to this data in some way, and that's really, really true in Rust because we have this concept of ownership, right? And so in this example, one is the owner of this data, and so we know Rust knows when to delete this data, when to clean up, when to drop the data associated with this vector when this guy goes out of scope. We know that. And so this is just a review of the last thing. And we talked about how you can, how Rust has built-in move semantics, how you can move ownership either by assignment or by function calling. So here, of course, we're taking ownership. And we learned that once you pass ownership away, Rust doesn't let you use that binding again. It invalidates you. So that's why this line right here is a compiler error, because one has been used after we sort of gave it away, right? And when we realized that, this kind of sucks because like I want to be able to use this vector after I compute the sum of it, like that's kind of annoying, right? So we came up with this pattern where we're like, well, let's write the exact same function here. This is still giving a sum, but it also is going to pass that vector back to us as an own type, and so we can sort of give and take that ownership. But again, like this is like really awkward, right? So the last video I used the word loan, and in retrospect, I kind of regret using that language because the Rust official language for this is the opposite. So there's a loaner and then there's also a borrower, right? So in Rust, the way in which you sort of loan out, or preferably the way in which a function can borrow some data is through this concept of references. And we'll take a look at that in the next program in just a moment. So it is possible to sort of not have to do this and allow parts of the program to not take ownership, but also still like read and write to that data. So anyway, this is mostly a review. We'll just keep moving on after this.
Yeah.
Okay. So here we go. So this is just almost exactly the same program. So we have this sum function, right? And it computes that sum exactly the same way. Actually, before we get into this, I did want to just briefly talk about this. This is
I was going to ask about that too.
This is potentially some new syntax we haven't used. I can't remember if we have. So Rust has built-in support for closures. This is kind of like, I think Ruby has a very similar syntax, but it's like an anonymous function. They do have some special like nuances to them in Rust, and we will not be delving into that too much in this video, but essentially what this is doing a reduce, right? So you have this vector and, we're iterating over it. We're starting with a sum of 0, and then we're just accumulating up a sum, right? So anyway, this is exactly the same function, and maybe we can actually just even pull that up. So this is 1. So let's make this a little bit bigger so that you're not covering it. So this is actually the same code as this over here, but here I've called it own vector because the type was an own type. But here I've called it borrowed vec. And it's exactly the same code. The only thing I've changed is I've added this little ampersand. So maybe if you're a C or C++ programmer, you're used to the ampersand meaning sort of address of. And that actually is a pretty good intuition because what we're doing here is we're saying when we call this function, we're going to allow this sum function to borrow this by essentially a pointer. Right, so let's look at this example of how we actually utilize this, right? We have this vector 1, 2, 3, and I'm going to create a reference explicitly here. So I have this new binding called ref to vec, and the value is an ampersand vec. So I have essentially taken the address of that vec and stored it in ref to vec. And so I've explicitly written the type here. You normally don't have to do this. Of course, Rust has a type inference, right? But I've written it explicitly to say that, the type of ref to vec is an ampersand vec I32, which is a reference to a vec of I32. And so that allows me to call this reference sum because it takes a ampersand vec like this, right? And so now it's actually possible for me to do this line right here without a compiler error. I'm allowed to continue to use vec in this scope even after I have taken this sum, and I didn't have to do this awkward tuple thing any longer. So just to be very, very explicit, essentially what we have done is we have created a way for us to not take ownership of something, not move it, right? We have not moved vec anywhere. We have just made a piece of data, which is essentially a pointer, without moving, right?
That
And
line,
this,
you're just trying to be explicit about what you're passing, but in reality, this could even be cleaned up to just pass that ampersand vec through, right?
correct. Another way to write this exact same line, and I will do that now, is to just say ampersand vec, right?
So that gets around that whole kind of awkward ownership problem that we had in the other example.
Correct. This concept of allowing us to take reference. This is where we do the taking reference. That operator there, that ampersand, allows us to sort of loan out, or preferably, I guess the language would be reference some borrows it from us, right?
Yeah.
Okay. And of course, there's an additional little wrinkle here, and this will become more important in the next part of this episode. But there's a second kind of reference. There's actually two kinds of references. There's a mutable reference, and it's written this way. So you say and mut, and then the type that you want to reference, as opposed to this up here, which is an immutable reference. This is the correct name for it. This is what you will see in the Rust literature, et cetera, is mutable versus immutable reference. And basically, essentially what this is it's similar to, but not exactly the same thing, just intuitively to making something mutable. I'm not allowed to push into this vector in this function because I have tried to do it with an immutable reference. And let's actually compile this program and just see what the Russ compiler is complaining about. Cargo run. This is bin 2, I believe. And so what it's saying is, help maybe you can't see this because your face is in the way, but now you can probably see it. Maybe, I'm not sure. It says it's an and reference, and we can't do it because we're trying to borrow it as mutable. And so it's actually suggesting we change the kind of reference. It says, try making this a mutable reference, and it might allow it. And so that's what we've done here. This is exactly the same function, just with a slightly different type. And to be very clear, this is part of the type, right? It doesn't necessarily have anything to do with the binding or anything like this. No, this is the type. It's a mutable pointer or mutable reference to a vec of i32. It's an immutable pointer to a vec of i32, right? So anyway, this won't compile. We could just delete it. And so here I'm just doing some basic stuff. I'm just calling this multiple times, and I'm summing, and so I expect a slightly different number here. So once I have deleted that thing, this should actually run. So it's 1, 2, 3, and then we sum it up, and now it's 8 because I've added 2 more in there, right?
Great.
Nothing too crazy there, right? Seems pretty reasonable.
Yeah, I think I'm following.
All right. Moving on. Okay, so Rust has, of course, a pretty strong emphasis on safety and rigor of your program. So if you come from a C or C++ background, maybe even a Java background, to be honest, you're already getting a little bit nervous, right, about references and pointers because they can get scary, right? And the reason they can get scary is a couple things. They can have problems with is the data that they're pointing to still valid? And so Rust actually has a specific rule built into the compiler for references, and that's this first rule here of references, that references must always point at live data. And so back in the previous part of this web series, the previous episode, we sort of talked about how Rust has a concept of the lifetime of values, right? In the sense that it was using this concept of lifetime to deal with ownership, right? The lifetime of a value was around scopes. But it also has a concept of lifetimes associated with references, like how long is the pointer alive for, right? And so it makes a rule and also guarantees for us at compile time that if we have a reference to something, we can always dereference it safely. It's always live. It will always be around and safe to point to. And so actually I have a function here that sort of demonstrates that. So this is a function. It tries to return a reference to a vec of i32. But if we look at the body of this, given what we know from the previous episode, we know that deadvec is the owner of this big vector here. And we know that once this goes out of scope here at this curly, the Rust will drop it and sort of delete the data. And we've tried to return a reference to that thing that is essentially going to be immediately deleted. And so whoever calls this function is already in trouble, right? Because they're going to potentially dereference a pointer that is to data that's no longer dead, or is no longer alive. So if I try to compile this, what are we on, 3 here? Oops, I need to say run.
Maybe run or something.
There we go. So it's complaining about a couple things. We had some things in here from before. Let me fix this real quick. And it says, oh, okay, this function's return type contains a borrowed value. So here's the borrowed value. This type is a borrowed type, right? But there is no value for it to be borrowed from. It's saying that the value that was associated with that reference is gone, right? There's also this kind of cool thing. I don't think we've shown this yet. So Rust, if you invoke the Rust compiler yourself with Rust C and you say explain, and then you type in this like error code right here. Yeah. So I think, let me see if I can copy and paste. This seems Rust C. Oh, look at that. I have it. So I just typed in this error code. And so it'll actually like give you this like documentation.
Well, that's nice.
And sort of help you explain why this is an error in the general case, right? And so maybe it might even have some links into it to like maybe, oh, look, here's a link to the Rust book or self or whatever. And so you can kind of get a sense of why Rust is complaining about certain errors. So anyway, it won't let us do this. And so I think officially this is called a dangling pointer, right? Dangling pointers are bad. Rust at compile time sort of ensures that you don't have that.
Yeah, I think you see stuff like this with other languages, maybe with pointers where you reference the thing that you're pointing at and or maybe release it and then you use it again later.
Yes.
So it sounds like with Rust you're getting like compile time.
Correct.
Of warnings or errors, I guess.
Right, and this is, by the way, not the only solution to this, right? Like a lot of programming languages, garbage collectors, right? As long as there's a reference alive, the garbage collector won't delete it. So, of course, Rust doesn't have a garbage collector, so it has to enforce this a different way if it wants this kind of rigor, right? Okay, and so the other rule with references, and this has to do with data races, is that at any one time, you can have either, and these are mutually exclusive, right? So you can have one or the other, but not both. You can have exactly one of those mutable references, or you can have as many immutable references as you like. And so this actually might sound quite familiar to you if you've ever used like a read-write lock. So what this is really doing is ensuring that sort of one piece of code can sort of has exclusive access to data. So that would be like this case. It's an exclusive access kind of thing. While this is more non-exclusive access. And actually, way back in the first episode of this web series, when we tried to make a program multi-threaded, actually the rule we were really violating was this one here. We were trying to pass multiple mutable references to essentially each thread would get one of these. And Russ was complaining and saying you can't do that. And so actually this is right here, this is what gives you compile time safety against data races, actually, which is a fairly unique feature. I don't know too many other programming languages that offer this, at least in the same way.
Yeah, I haven't heard of them.
Yeah. So so these are just some functions, I think, from the previous thing. It's just, this is a thing that takes an immutable reference, and this is a thing that takes a mutable reference. And this program down here actually doesn't compile because we have violated this second rule. So let's actually run this, compile it. Cargo run bin 3. So if we actually take a look at this, it says, oh, we have this vec thing, and we took a... oh, actually, this is some old code that I was messing with. Let's fix this so that it gives us the right error we want. So what it's saying is, we took an immutable reference to that vec right here. We have this ref3 thing laying around. And then somewhere later in the program, we tried to also take a mutable reference at the same time. And then it said, oh, you can't do that. You're not allowed to have, as we said, you're not allowed to basically have both of these at the same thing. So let's just more concretely look at this program, right? So we had a bunch of these immutable references laying around, and that's totally fine. You can have as many of these as you like. But then right here, we also tried to take a mutable reference to vec, and Russ complains about this. So I do want to point out something real quick, though, which is that and this is kind of confusing potentially, but actually is really awesome once you get used to it. If I comment some of this stuff down here out, this actually compiles. And you might be thinking to yourself, like, how is that possible? like, because I just told you that you can only have like either a bunch of immutable references or a single mutable reference. But actually, this is Rust getting smarter. So this, as of like 2-3 years ago, this was still an error. But what is actually happening is Rust is a little bit smarter, and it's recognizing that even though we have a bunch of immutable references around, we don't use it after like this line. So even though we do take a mutable reference at the same time, we don't use the immutable reference after we took that mutable reference. So that's why uncommenting these lines makes this complaint, is because we've used this after that. So this is actually an example of the compiler getting a little bit smarter, because, by the way, this is a totally safe program. As long as I don't do this, this is totally safe. And so a lot of new Rustian programmers maybe 3 years ago might have ended up writing programs that boiled down to this. And they're like, wait a minute, this should be safe. Why doesn't this compile? And actually now it does. So I think there will be a whole class of Rust programmers who start using the programming language in the last year or so who don't even know that this used to be an annoyance thing, because Rust compiler is just getting better. At the very beginning of the episode, we did talk about this idea of a pessimistic compiler versus an optimistic compiler. So if you're not familiar, essentially the idea is if you have an optimistic compiler, you're essentially saying, well, all programs that the compiler complains about are broken. But there may be some programs that the compiler doesn't complain about that it is broken for, right? So it's sort of optimistic in the sense that if you get an error, there's a problem. But if you don't get an error, you don't, right? Most compilers, or most rigorous compilers, I should say, I guess all rigorous compilers are pessimistic compilers. And Rust is definitely in that genre, which is to say that there are some programs that actually may be okay, may be valid, but Rust will still complain. But at the very least, you can know the opposite, which is that if Rust isn't complaining, then you have a safe program, right? Okay. So anyway, that's an important note, and I think this is definitely a philosophical thing that certain people might feel differently about, and it's an important thing to think about when you choose Rust as a programming language or another language like Rust. How much do I want the compiler to complain at me? Do I think I'm smarter than the compiler, right? All right. So anyway, that's pretty cool, right? Okay. Does this make sense, Noah? This is probably...
Yeah, Noah, I think I got it. Yeah, I mean, it took me a little bit to get that kind of rule thing. And then, I was a little surprised too, that when you showed that you could comment out the later code and then everything was fine. But,
yeah. And you used to have to fix this.
More about thinking about what the compiler is inserting. I guess it's inserting the drops before that or something. Or
yeah. So remember that yes, you're right in the sense that philosophically it thinks of the drop as happening earlier, but there's actually no code that's going to run in this case, because these are just pointers that will be just released when the stack is over, right? But you're right. You're totally right on a philosophical sense, right?
I see. Okay.
Yep. Yes. I think that most people also, this is sort of where they get into, I don't want to say get into trouble, but I think when people talk about the Rust tax and how difficult Rust can be, it usually they run into borrow checker errors, and they try to essentially do this and I don't understand, So usually I think this is the thing that you kind of have to gain some intuition. I don't think too many people run into this. That's pretty obvious. And in the cases where the Rust compiler complains that you're oh yeah, I really did do that. That was dumb.
Yeah, it looked like you really had to.
Yeah, you kind of have to almost manufacture it, at least in my experience. But this one you can run into. And by the way, there are ways to get around this. For instance, since Rust you were asking me when is these blocks useful? It's you can kind of create blocks for yourself. So these references only live up until here. And so you can actually, this is kind of the old way you used to fix this, was you would just create blocks and sort of make sure that your immutable references actually died, before you did this, so to speak, right? Does that make sense? Now this is complaining for a different reason, but
I see.
It's complaining because it's out of scope, right?
That's a different problem now.
Yeah. Okay. This is let's see, it's undefined variable name, right? Cargo. It says local variable. It doesn't exist, right?
Oh, okay, cool.
Yeah. Okay. Right. Yes. Let's keep moving then, right?
Yeah, I'm good.
All right. So this is so I was kind of thinking to myself, and I know that you and I discussed this a little bit earlier. When I was sort of writing up the notes for this, is like Rust programs and idiomatic Rust typically uses method syntax. So up until this point, to keep things simple, I have not been using methods at all, except the sort of built-in ones. But if you define your own type, as we have sometimes in the past, there is a syntax, which is this impl, to sort of attach functions to your thing. And that allows you to use the method syntax, right? And I just want to be very clear that this program, besides the new syntax, it doesn't do anything new, right? There's nothing in this program that we haven't learned or don't understand why it works the way it works. You can almost think of it literally as just some syntactic sugar, some like nicety, some idiomatic. Like again, this is very idiomatic in Rust to use the methods on your types, but it doesn't do anything special, right? And so we're just going to very quickly run through this, but I think this is important to recognize because you will be using types in Rust, like built-in types in the standard library that obviously have methods, and to understand what their types are because of these references and ownership and all this stuff, you're going to want to know this stuff, right? And so I wasn't quite sure where to put this in the web series, but I kind of threw it in here because like we just learned how references work, and now we're going to see how we can use references and ownership and all the stuff we've already learned to create methods, right? And so if you have an impl block and you name your type, so these are all of the functions that are going to be attached to a vec accumulator, you can attach methods, right? And so how I know these are methods is this is like syntax. It's not just like a special name or anything. Is they have this special binding called self. And you don't have to put the type here. Like I don't write vec, like I don't do that, right? Self is just the vec accumulator you're working with. And so there's 3 ways to write it. As we know, you can just write self, which is the owned version, right? So this method takes ownership of the self. You can write immutable references, so ampersand self. And so this function doesn't take ownership. It just borrows immutably self. And then you can also, of course, mut self, and that's a mutable reference to the vec accumulator, to self, right? And so these are exactly the same as all the functions we've all been writing. They just allow me to, when I have one of these vec accumulators, to actually call methods on it.
That self is always the first parameter, right?
Correct.
If I wanted like another param, I'd have to have it as the second one, right?
Correct. So like, for instance, maybe I want to do like also, right? Maybe I want to put another I32 in here, and then I could just do plus also, something like this. You can have as many arguments as you want, right? It's just like kind of like an implicit kind of argument, kind of type, right? That's really all this means. So let's do that. So this compiles. You can also, this is related, but this again teaches us nothing new. You can also just put, I think they're called associated functions with a type. So that's when we use this : syntax. So we haven't created the vec accumulator yet, but maybe we want to create one. Oftentimes you see idiomatically people will use the new function, right? So here's an example of the new, and that just returns self. So capital self is a special type inside of impl blocks. It just refers to the type that you're talking about. And so this just returns like a new vec accumulator. Also, you'll see functions like from. So it's like, I want to create a vec accumulator from another vector. Like this is how you would do it, right? Here's that right there, right? And so again, this teaches us nothing new. I do want to just briefly show why this program right here is actually a compiler error. Let's just like do this, right? So this is 4. So what it's actually saying is we have tried to use a value, which is a cum, after it has been moved. And so if we take a look at the type here, right, just like we learned back in the previous episode, I have called a method here that takes ownership of self, right? So a cum has been moved into this invalidate method. And so that means that after that line, the accum binding has been invalidated. I can't use it anymore. So, this is nothing special. This is exactly the same thing we've learned is that, here's this method that essentially takes ownership and like invalidates the calling scope, right? Yeah. And so
this would be similar to the regular function.
It's basically exactly the same. Yeah. Yeah, and I don't see this type too often. It's pretty rare. Most of the time, you'll see this or this, because usually methods don't like destroy or invalidate a thing. You want to keep using it, even though you're using methods on it, right?
Sure.
Although there is one example I could think of, which is on the vector, which we've been using all this time. There's a method you can call called into iter. So we've been calling iter, but there's another one called into iter, which is essentially saying I want to invalidate the vector because I'm turning it into a vector, or I'm sorry, into an iterator in such a way that like that vector is no longer valid. I'm sort of throwing it away and like maybe disposing of it into.
Don't use the original.
Right. And so this is a pretty useful tool when you need it, which is to say that like writing a function this way is explicitly telling the caller, hey, once you call this thing, like consider your instance of this thing like no longer good, right? For whatever reason, right? Anyway, so that's that.
Okay.
There's really nothing special here. We know all the rules of how these works and why they work. It's just like it's a convenience syntax, really.
Cool.
Okay, let's keep going. 5. So this is sort of a bonus section. So there's another kind of reference, or maybe another kind of pointer would be a slightly better way to say it. But and this is called a slice. And so let's take a look here. So we had we had one kind of reference like this, which was like let x equal ampersand vec, right? So the type of x here was a ampersand vec, right? We know this already from what we've learned, but it may be the case that we want to not just reference the vector as a whole, but we want to reference like a small sub part of it, right? Maybe it's like a vector of like 5 items, and we just want to reference like maybe the 3 middle ones or something like this. This typically comes up a lot with strings, right? Because like sometimes you're just like, oh, here's like the part of the string that I'm interested in, right? And I think in maybe the second or the third episode, we wrote like a parser program that was actually kind of doing this, right? It was like, maybe iterating through a string and sort of slicing away the parts of the string that we were interested in, right? We were sort of throwing it away. So there's another kind of reference, which I'm actually doing down here. You write it this way. You say ampersand just the same way as you would with a regular reference, but you put these brackets, and then inside the brackets you have like a range. So for instance, here I'm saying I want to reference every part of the vector except the first. And so this is a inclusive number. I'm saying give me the first, and beyond. Here's another example. I'm saying only the second number. So the second number is 1, and it's exclusive on the top part of the range, right? Mm-hmm. And so let me I think this is currently not compiling. So let me just comment this so it will compile. And I can actually demonstrate this. Cargo run bin 5. So here you can see I started the vector with 1, 2, 3, but I printed just the first item. Here's only the second item, right? 2 and 3. Only the second item is 2. Here's exactly the same time. Just like implicit parts of the range, right? So here's everything up to, but not including the second item, right? So that's 1 and 2. So slices are useful. And so what they actually are, like in a literal sense, is they are a pointer to like the first item. And also, I mean, by the first item, I mean the first item that's in your slice, not necessarily the first item that you took from the data, right? But it's also a length, right? And so those two pieces together will allow this slice to know what like segment of memory is like useful to it, right? In fact, as I said, this really comes up a lot with strings. So there's actually I don't want to say a special syntax, but like a special shorthand for this, which is this and stir. So we've been using this all along. This is actually a string slice. Right, it's not a string; it's a string slice.
And when you get these, so a couple questions actually.
Yeah, absolutely.
These, you're getting a kind of a window on the existing.
That's a perfect word for it. Yes, it's a window. Yes.
Okay, cool. That's similar to I think to the way Swift did it also. And then the other question is, are there compile time checks on the bounds? Or are they
excellent question? Excellent question. There are runtime checks. Okay. And so due to like how they work, sometimes those runtime checks will actually be compiled out. So it is so you're right in the very like sort of the very pedantic sense that like, yes, these will if you like try to index at like 5 and there is no 5th or something like this, that will be referenced in types or potentially a runtime error. It'll say like it'll panic in some way depending on how you actually did that indexing. But in most cases, a lot of times what you're end up going to be doing is like maybe like iterating over this slice or whatever. In which case, the compiler will recognize like, hey, this iterator can't ever be out of bounds, so I don't need to like put that bounds check in, and it'll just like run the sort of hyper efficient code. And that's interesting for people who are like very performance oriented, right? They're like, oh man, Russ has all this rigor and like puts in all these bound checks for me, and I have to pay all this cost, right? Well, not all the time. In fact, most of the time you don't, right? But excellent question.
But that's the program would just stop if I was out of bounds. Is that right?
It depends on how you did the indexing. So you can like there are probably quote unquote safe methods like index at or something, which would return an option, right? It may return you a sum or a nut.
Like you're doing it here though.
Yeah. So exactly. You're asking like, well, what if my range is out of range? It'll probably just go up to the correct length, right? Like maybe if this was like 20, like let's actually try it, right? Like what happens, right? So it compiled and it crashed.
Okay.
Right.
Cool. Oh, panicked. Okay, cool.
Yeah, right.
Cool.
Okay.
Sorry for the digression there.
No. It's a good question. It's an excellent question. Okay, so what we were talking about. Oh, right. And again, these slices, they come in immutable and mutable versions, just like references, because again, they're like a pointer, just like a reference, but they also have this additional data, which is a length. And they come with all the same rules. So you can have as many immutable slices laying around as you want, or you can have one mutable slice laying around, but never both at the same time. And that's pretty much it. Like the only additional thing that really you have to think about is this special syntax for them for stir. But other than that, they're pretty intuitive, right? Like if you've used other programming languages, you've seen syntax exactly like this, and it even has the same syntax as the references that we were just talking about in the previous part of the video. That you do an ampersand to take an immutable slice, and you do an ampersand mut to take a mutable slice. I do want to point out one kind of cool thing kind of here right at the end, which is that because of those guarantees that Rust makes about references and also slices, is that they can't ever be pointing to invalid data, right? So if we have a string here, right, and it's hello Noah, right? If I call this function on it, which is find first character, right? This is like iterating through the characters inside that string, right? That haystack, and it's finding the first instance of the character I'm looking for. And then it's returning me a slice to sort of that character and the rest of the string, right? Otherwise, it's returning me nothing, right? So this is actually very interesting because if I call this function, this slice that gets returned to me, which is again like a contiguous kind of part window of that string, it only really makes sense as long as that string doesn't change, right? So imagine at this time, right, the string is, hello Noah, right? So we expect the slice to be kind of this window right here. That's what this found O would be. If we try to like change it, like maybe we actually, instead of that, we just like clear it, right? We like delete it, right? We're essentially clearing out the string. There's no more data anymore. This like slice doesn't make sense anymore, right? Like it's actually pointing to data that doesn't exist. It's sort of become like out of date, right? And so actually, this is actually a compile error in Rust. And this is a common pattern that you'll see throughout Rust in libraries, in the standard libraries, that like they will sort of abuse slices and references such that they can make guarantees about how calling code interacts. Like we are not allowed to change this string until this found O goes away, right?
Gotcha.
And so that actually is a really nice property, right? Like our window into this string actually continues to make sense. Like if we returned like I here, for instance, like an index, like an integer, so to speak, it's very easy for that integer to get out of sync, right, with the string underneath, because the string can change at any time. But because we have chosen to return a slice, we actually like get more constraints, more guarantees about how our program is operating. And again, the reason this is an error, and this is kind of going, is we already know why this is an error. Well, we have this slice right here. We took an immutable borrow to something, and then we tried to take a mutable borrow to it, because that's what the type of the method clear requires. It's an and mut self. And so we tried to take an immutable reference to something while a immutable reference was still alive, right? And actually, just like in that program before, if I get rid of this, if I don't use that immutable reference, it's now actually not a compiler anymore, because the compiler was smart and said, oh, you're actually not using this anymore, so like actually this is safe. So again, it's trying its very hardest to be helpful to us, right?
Cool.
All right, I think that's pretty much it. One other real quick thing, this is just sort of as a side note, is that literal strings are the type reference string. We've been using them all along. So this is not the same type as this. That's something very different. Literals have to be, because Russ is a compiled binary, literals are like actually like encoded into the binary, and they essentially are just like a segment of memory, and they're immutable, right? So that's why the type of them is an immutable string slice, is because you're slicing a part of the binary, right? And it's an immutable part of the binary. You're not allowed to change that string because someone else might expect that exact string, right? Does that make sense?
I think so.
Yeah. This is just kind of a nuance that, like, beginner Rust programmers might be a little confused about, like, what's the difference between this and this. We took like 5 episodes to get here, so that we could even explain what a string slice is, and all this reference and ownership stuff. Like, this is crazy, right? But that's just an important note, is that if you have a literal, it's not a string, it's a stir, right? It's a immutable slice, right?
Okay. Cool.
All right, I think that's it, man. I think we have covered it. So I think that this episode is probably the toughest one of all of the episodes we've ever done. So, feel free to reach out to either me or Noah. I know Noah's on Twitter, or comments in the video. We'll try our best. The Rust book also has a good section on ownership, references, and slices. It's just another perspective. I tried very hard not to do exactly the same things as the Rust book, so that people who are watching this video could try both and maybe get some things from the Rust book and some things from this. My recommendation for this stuff is, get a sense of those rules, sort of memorize those 2 rules for references, but then, really just kind of start programming a little bit and try to get some intuition, because that's really what's going to help you, is trying to build some programs, trying to use these references and do real things. And then where the compiler will try to help you, right? It'll be like, hey, you can't do this. And then maybe over time you'll start to feel more comfortable with this. I would say that now more than ever, the Rust compiler is pretty good. There's most of the time when the Rust compiler complains, it's for real reasons. It's not just being like pesky. Okay. Anyway, anything else to add, Noah?
No, really. This was interesting though. Yeah. It's good to have, some of those insights too about like how the Rust compilers changed. So
yeah.
I think I could see myself getting stuck on those violating those rules.
Yeah,
so.
Yeah, and you'd be upset.
I think probably.
And I wouldn't blame you. Okay.
All right.
So I think with that, we'll call it quits. Thanks for watching.
Bye.